Okay, so today we'll try the microphone, and then you can tell me if it's actually better or not. I assume it's probably a lot better when I speak against the board. Yeah, we'll see. All right, so today we have the the short Friday lecture, but we'll try to make some progress. Okay, so we started talking about functions on Tuesday, right? So on Tuesday you saw, right? We started with talking about complex functions and differentiable functions, right? So we took, like, this will actually be the object that we're going to study the most, right? And these will be functions from the complex numbers to the complex numbers, right? And we defined the derivative, right? And this was a very important object. The derivative was defined exactly the same way as in the reals. Maybe let me clean this a bit better. Okay, so it's simply the definition that you're used to over the reals. Right, and of course the function is differentiable if the limit exists. Right? And the big difference here that we already saw a hint of the effects that this could have is that x can approach a from any direction, right? Well, we were over the reals, right? We don't know the reals, and you have a, sort of x can only come either from this end or this end, right? And we can even talk about the limit from one side, limit from the other. Over the complex numbers, really what makes everything so different is that x can approach from anywhere. And the limit needs to be consistent regardless of where x is approaching. Right, so and because you're dividing by sort of the number, right, x minus a, you're dividing by the vector of where you're approaching by. The fact that this always needs to be the same creates a lot of regularity, right? And this is really there's one thing that's important about complex analysis and thinking about complex value functions. It really is the fact that being differentiable on the complex plane is much stronger. And as we'll see, won't be just a local property. It will be much more. And if something is differentiable, it will imply that you actually know a lot about the function. For example, we'll have theorems of the type, if it's differentiable, say everywhere, and if you know what it is in just a small place, then you actually can extend it everywhere. Right? And if you think about functions over the reals, right? If you know what its value is, say in a small ball, and you know it's differentiable, you can certainly think about extending it in many different ways, right? But over the complex numbers, it turns out that being differentiable will be extremely strong, right? And this is what makes rise to almost everything in the theory, right? I guess is the two things: is that and the fact that every polynomial has a zero, and this, essentially everything can be traced back to this. Okay, and it's useful, like as I did last time, to think of, to write this limit in terms of x minus a and call it some kind of increment h. Right, and to think of things like this. Right, and we saw already sort of a surprising application of, or I wouldn't say application, consequence of this definition. Right, and one consequence of this definition was, let's say that, right, so I'll redo it because last time we did it rather quickly. But if we have some function over the complex plane such that, say, f of z is real for all z in the complex plane, let's say, or even in an open interval, it doesn't need to be over the whole complex plane, right? As long as it's an open interval, you can still do everything, right? Then you can think about what is f prime of a. And if you think about it in terms of this, right, it needs to be the limit of h going to 0, right? Okay, I'm just rewriting the definition. But now, of course, I can take h to be a real number, right? I often represent real numbers by just t, right? Because t's are usually reals. I mean, they're good to parameterize curves and so on. Right? If I take this to be a real, then, the limit needs to be the same. Okay, let me maybe put this in another, right? Just to see this is separate. Right, and this equal corresponds to this one. right? Then I have this. It's the limit of t going to 0 of f a plus h minus f of a over t, right? But if the function is real, then the function value here is real. We're subtracting another real, and we're dividing by a real, so this is real, right? Right, on the other hand, we could also have taken h to be a purely imaginary number, right? We could have taken h to be just I times the number t, right? Where t itself was real. Right? We're just taking we're thinking of h, right? Or you can think here of a, and we're approaching it over here. We're approaching it from the purely imaginary line, right? And in the blue example, we're approaching it from the real line. And the limits need to be the same, right? Otherwise, the limit doesn't exist, right? And so if I compute the derivative approaching this way or this way, it must be the same, okay? So I do it over the blues, and I get the real number. Let's do it over the, let's do it over the imaginary line, see what we get, right? What we get, let's just write. We get limit as t goes to 0. And now what we get here? We get f of a plus it minus f of a over it. Right, but now this is real. We're subtracting another real, dividing by a real, but also by I. Right, so in particular, this is equal to, say, minus I times, okay, I'll write this very small. I'm just writing the same thing. Right, so it's in particular because this number is real. This is purely imaginary. Right, what I mean by purely imaginary, simply that it's a multiple of I. Right, so this means that this number here needs to be both a real and a purely imaginary number. In particular, what all this implies, right, so all this observation implies that actually f prime of a needs to be 0. Right? And we saw this, rather fast last time, but even though this won't be, necessarily a theorem that you'll use very much, the idea here is very important, right? What just happened is very important, and this will be key, right? And this already gives you a hint that, for a function to be differentiable is extremely strong, right? Because in particular, if you think of a function from the complex plane that just takes values over the reals, it actually needs to be constant. Right, so very natural things like the norm squared, say, right? This feels like a very, very nice function, right? If you think in terms of real analysis, this is a rather nice function, right? It's some parabola, looks very nice, completely smooth, completely everything, but it cannot possibly be differentiable from the viewpoint of complex analysis, right? And so this difference between what differentiable means is really the key to the theory. Okay? And so now what we're going to do is we're going to transform this argument. Right? We're going to use this idea that the derivatives need to match whether I come from the reals or the imaginary numbers, and we're going to make it into something that we can actually use. Right? We're going to use the fact that these things match not only in functions that take values over the reals, but any function, and we're going to get a bunch of differential equations involving the partial derivatives if we think of the function going from R2 to R2. Right? And this will give us the celebrated Cauchy-Riemann equations. Right? But the idea of what we're going to do is already completely present here. Right? We're just going to be more careful in keeping track of all the definitions, all the partial derivatives, and so on. But the key argument is already here. Okay, so let's do that. Okay, so just some quick definitions. Okay, so if f going from, okay, let's say some open sets and domain to C, okay, I oftentimes just, right, and we want it to be open. Okay, you'll see some of these, you'll remember some of these topology from real analysis. You'll see it also some in exercise lectures. But I'm not going to worry for now so much if it's defined in an open set or all of C, because the statements we're going to say for now are completely local. So then it's all the same. But okay, let's say we have some function from the complex numbers, right? If it has a derivative in all points, in every point in D, we say that f is analytic, okay, or that it is holomorphic. Right. These are essentially used interchangeably. Right. And this should already be hinting, right? Over the reals, a function being analytic is much stronger, right? It has to do with it matching its Taylor expansion and so on. And so, here, right, it's already hinting that being differentiable is already going to mean a lot more, right? This is the name that we call it is already quite telling, okay? And indeed it will. Okay, now of course you need, right, some housekeeping is in order. We better make sure that if a function is analytic, then the sum is analytic, the product is analytic, the quotient is analytic, and all this. I'm going to save you from, writing down all those limits, but this is a very good exercise, right? So if f and g are analytic, then, right, f plus g, f times g, and f over g, of course, if g is not 0, in a domain, are analytic. Right? This is very good homework. I mean, not, these are the kind of things that if they're not true, then there's something wrong with the theory, right? So they need to be checked, but it's exactly the same. It's exactly the same thing as for as for the reals, right? So I won't do this. Also, I mean, maybe one thing that I should do, because being analytic seems a little different over the complex numbers, is I'll do one point of this sort of housekeeping, and one is to show that if the function is differentiable, then it's actually continuous. But that's also pretty obvious, but okay, let's do just, so if f prime at a point A exists, right, and what does this mean? This means that f prime of z, right, is equal to the limit. I'll try to use the same notation as in the book as much as possible, so that it's easier for you to go see. Right, but so what this means, if this limit exists, since this thing goes to 0, then this thing also needs to go to 0. Right? I mean, you can write it a bit more carefully, but we must have that the limit of h going to 0 of fz plus h minus fz, right? This minus h f prime z should go to 0, or I should do this differently maybe, right? But this should be the same, as the limit when h goes to 0 of h times f prime of z, right? But of course, this limit goes to 0 because h goes to 0 and this exists, right? And so therefore, this, we know that this limit needs to go to 0, and so f is continuous. Okay? This is, just exact same thing as over the reals, and with arguments of this type, you can show all this stuff about the functions that you can create out of two analytic functions. Okay, so now let's do something interesting, which is let's try to understand, it's clear by now that if you take this limit coming from the reals or the purely imaginary, they need to match. However, they seem to tell you different things about the function. And so the fact that those match will force the function to satisfy certain properties. Right? And so what we're going to investigate now is which properties are these. Right? And so let's do that. Okay, so let's say we take f analytic. Right, so a function from C to C. Right, so I write, I've used notation a little bit sometimes. I write f to C, but again, if it's just defined on an open subset, it's perfectly fine. Okay, it's just that in the beginning, I want to make it clear that it's a function that takes complex numbers and not a function that takes real numbers. Okay, and now we want to understand what needs to happen to their imaginary and real parts, because we're going to have those limits be taken in both the real and the imaginary, the real and the imaginary directions. Right, and so we're going to write f of z as u of z plus I v of z. Okay, and so these functions, right, this function u and v are functions. They go now from the complex numbers to the reals. Right, but I'm not going to ask that they are analytic themselves. Right, it's just, we'll think of this for now as completely, just multi-calculus differentiability. Right, fz will be analytic. This will force something. Well, I know it. I can just take the real part of f and the imaginary part of f, and they'll be differentiable in the sense of real functions taking two real numbers and outputting one real number. They are differentiable. Okay, and we'll think of z, as x plus iy, and so we can really think of u of z as, okay, there's a bit of abuse of notation, not a lot, but a bit. I'll take f u of x plus iy. I'll represent it as u of xy, right? Because I want to look at partial derivatives, and I want to be able to say what they satisfy, and the same thing for v. Right, so really, I'm going to think of these. I'm going to think of these functions as functions that go from R2 to R. Okay, so let's start. Right, let's take. Maybe I should keep with my drawing. Let's see what we get if we do. Okay, I'm going to approach from the reals. Okay, what I'm calling H. Again, so what do I get? F prime of, at a point, z is equal to the limit as t goes to 0 of f of z plus t minus f of z, right? And this limit needs to exist over t, right? But if I now think, of the function f, I could also think it as a function that is from R2 to R2, right? Taking values in x and y. If I think about it this way, then this really is just a partial derivative of f with respect to x. Right? I'm abusing notation a little because I don't want to introduce more variables. Right here, I'm thinking of f as going from C to C, and when I write these partial derivatives, really what I have in mind is f going from R2 to R2. Right, so whenever you see partial derivatives, that's what I mean. I'm doing sort of an identification between the two. Right, so in some instances, I'm thinking of some, right, where it receives the real and imaginary part and outputs the real imaginary part. Or actually, no, for now, I'm actually only defining it as going to C in this language. Okay, so what is this? Right, because of how to define things, this is just partial derivative of u with respect to x plus partial derivative plus I partial derivative of v with respect to x. Right? So I take the partial derivative of f with respect to x, but f is equal to u plus iv, so I just get the partial derivative of u with respect to x plus I times the partial derivative of v with respect to x. Right? And now these functions are legitimately functions from R2 to R. Okay, so now let's do the other thing, right? Let's do the approach from the other side. Okay, so let's take h approaching from here. So we right, because I like using the letter t to represent a real, so I'll use h being it. Right, and now what do I have here? Okay, I have that, right, same thing, f prime of z, right, needs to be equal to that, right, that is the limit of right? But if you think about this, right, this is 1 over I, right? This is just 1 over I times the partial derivative of f with respect to y. Right? Because there's this I here. I'm changing the I coordinate by t, right? And so this is just 1 over I right? And this is where things sort of get interesting, right? Because when you take a partial derivative, if you were thinking of the input as just receiving x and y, then when you were to take some partial derivative, you would divide by how much you fluctuated, how much you changed in y, the increment in y. But here, because of algebra and the complex numbers, you actually divide by I times t, right? By I times that, right? And so what you get really is 1 over I times this partial derivative. Right? You bring the I outside and you get exactly that. Right? And so in particular, now we can continue with this. What we get 1 over I times the partial derivative of u with respect to y plus I partial derivative of v with respect to y. Okay? Okay, so if you don't like very much the fact that we're taking the function f from R2 to C, and it's creating some confusion, you can just expand f in terms of u and v and go straight from here to here, right? And you could just ignore this. Because if you write f as uz plus ivz, you would go straight to here, right? But it'll be useful to use this notation too. Okay? Yeah, if there's any question, please, write on the chat. And now here we can recover very quickly the proof of the statement we had before, right? Because if f went only to the reals, then this meant in particular that vz was 0, right? And so if vz is 0, then right here what we get when we take the derivative approaching from the real axis, we get that it's a real number, right? Because v is 0, so this is a real number. And when we do it here, this term disappears, and we get 1 over I times a real number, which is a purely imaginary number, and we get exactly the conclusion that we had before. But because now we kept track of more terms and kept track a bit better of what was going on, we're going to get nicer things, right? Because we actually get some relationship between the real part of this needs to be equal to the real part of this, and the imaginary part of this needs to be equal to the imaginary part of that, right? Before we were using that with just 0. Now we can use it with any number. And so what we get, okay, let me write this a bit nicer. Let me put the 1 over I inside, right? 1 over I is equal to minus I. So I get minus I u plus I times 1 over I is just 1. Okay. So what does this mean? Because, let me do it, right? Because this needs to be equal to this. Right? This means that the real part of it needs to be the same, and the imaginary part of it needs also to be the same. So we immediately get some implications, right? We get that this number here, let me try to use the same college, right? This number here needs to be the same as this number here. And this number here needs to be the same as this number here, with the minus. So, right? And so immediately we get that the partial derivative of u over x needs to be the same as the partial derivative of v over y, and the partial derivative of v with respect to x needs to be equal to minus partial derivative of u with respect to y. Okay. And these are the celebrated Cauchy-Riemann equations. Right? And most things that we do in complex analysis, most conclusions we're going to take, they can somehow be traced down back to this, right? We won't be useful to keep, it won't be useful to prove every statement that way. We're going to just take, right? We're going to make certain implications and build on those and so on, but almost everything can be traced back to here. In particular, right? So let me give you, some in sort of foresight, which is that you may have seen, right? One thing I talked about was that there was this very important theorem in complex analysis that if you integrated around a curve, it was a closed curve and the function was nice and so on, these integrals were always 0. Right? That basically one way to view this is that if the function is a primitive and you integrate, then it should be like the value of the primitive in the end of the path minus the one at the beginning. But if the beginning and the end are the same, you should get 0. Right? And this felt a little, maybe not so mysterious after the primitive, but still it's kind of mysterious because why should they have primitives and so on and so forth. But here it's already kind of telling that there's some kind of differential equation at play, right? And if you think of something like Green's theorem and Stokes' theorem, when we integrate a curve, integrate some function on a curve versus integrating it inside, right? You have theorems that tell you how the integrals relate, and the fact that the Cauchy-Riemann equations are actually one way to explain why the integral around is why the integral inside is 0. Or the integral around the curve is 0. Sorry, what you'll get inside will be 0 because of the Cauchy-Riemann equations. That's one way of approaching these Cauchy theorems. It's not the approach we're going to take, and also it can already sort of start hinting at the fact that complex functions are very special in the sense that if I know what they're doing in a small open set, oftentimes I can extend them anywhere. Right? Or if I know what they're doing in sort of a boundary set, then oftentimes I can understand what they're doing inside the boundary. Right? And you may remember these kinds of things from differential equations, right? In physics and in applied math and so on, people do this all the time. Right? There's some physical system that needs to satisfy some differential equations, and you know what it's doing in the boundary, and you want to know how it evolves over time, or just what is its steady state or something of this type. And if you know what differential equation it satisfies, oftentimes you can find a solution. There's only one solution, subject to some kind of boundary conditions. Right? And so because differentiable functions on the complex plane will satisfy some kind of differential equation, it's kind of clear that they should behave, right? perhaps if you know what they're doing somewhere, you can figure out what they're doing somewhere else, just because they resemble a lot like some kind of, physical system in steady state or something like this. And indeed, this will be completely spot on, right? But I hope that this is already giving you some intuition of what makes complex functions special, right? And connecting with some things that you've seen before, in applied math and physics and so on. Okay, so let's see a couple. Let's push this a bit further. Let's push this a bit further and see where we can go. Maybe I'll leave the Cauchy-Riemann equations on the board. Okay, so in particular, because the derivative is given, right? The derivative is given with respect to, right? The derivative approaching from the real axis and the y-axis is the same, right? The real axis and the imaginary axis. Then we can just write, right? We could even write things like, right? The derivative of f is simply right, because if it's differentiable, then the derivative can be written, and it's just the derivative over the real axis. Right, so for example, there's already kind of a few interesting things you can do. Right, so let's say that I look at what the derivative of the norm squared is. Okay, so let's just write that. Right, this is a complex number, so its modulo square is just the sum of the square of the real part and the sum of the square of the imaginary part. Right, we know this function is not analytic, but we can still try to work out what it is. Right, so now let's use Cauchy-Riemann. So let's keep one of them being u, partial derivative of u with respect to x, and switch the other one to being the partial derivative of v with respect to y. And do the same thing here. Right? And now we swap the other one to be u with respect to y, but has a minus sign. Okay, but this you might recognize is exactly the Jacobian of the function if we think of the function going from R2 to R2. Right? In particular, this is the same thing as taking the determinant of x and you let's see if I don't. Okay, which is exactly the Jacobian. Right, so if we take the norm squared, the size of the derivative, then we're getting exactly sort of the size of the derivative that we knew from multidimensional calculus, right? Which is good. Okay, let me try to do one more thing before we end. Okay, so later we will see. So for now, it's not, I'm gonna cheat just a little bit, but later we'll see that if a function is analytic, then we'll actually have, you can take the derivatives many times, right? Analytic functions will have this special thing that if you can differentiate them once, you can actually differentiate them more, which is not, of course, not true for real, for functions in real analysis, right? But over the complex numbers, once it's analytic, we're gonna be allowed to take more derivatives. Okay, but for now, let's just say that you can take two derivatives of the function. Okay, so let's look at what, what the Laplacian of u is. You may remember the Laplacian from differential equations or physics or some real analysis. Right, so what is this? I take the second derivative of u plus right, I take the second derivative of u with respect to the first coordinate times the two derivatives of u with respect to the second coordinate. Right, this shows up in like heat equation and diffusion processes and so on. And in particular, if a function has its Laplacian equals to 0, then we call it a harmonic function. Right, they correspond to steady states of many, many processes in physics. Okay. So let's try to write this. Okay, so let's try to write this in a bit of a different way. Right, so I have the derivative. Right, I'm assuming that I can differentiate u as many times as I want. Let's say it's C2 because I'm differentiating it twice. Okay. But we'll see if f is analytic, that will be the case. Right, so I have this. Right, I'm just taking the derivative with respect to x, and then I take the derivative again. Right, but what is this? I can replace ux by vy, right? Because u is I'm imagining that f is analytic, right? I can write fu plus iv analytic. Right, so this is the derivative of v with respect to y with respect to x. Okay. Okay, so I just differentiate twice, right? But if u and v are both differentiable twice and continuous, then it doesn't matter if I differentiate first with respect to x or first with respect to y. We know from multivariate calculus that these partial derivatives are the same. Okay, so now let's see what happens with this term. Okay, we'll do exactly the same thing. Respect to y, again with respect to y. But what is this equal to, right? This is equal to minus the partial derivative of v with respect to x. Derivative of y, right? And so what this is equal to, this is just equal to minus, maybe let me go under here to not be crowding this too much. Okay, so we get here minus, right, x or y, x, right? But because those things are the same, right, we know we get here the two derivatives, right? We get here the partial derivative of v with respect to x and y and with respect to y to x, but we can swap them because if a function has continuous derivatives, then the partial derivatives are the same. And so this means that this must be 0. Right, and so this is also an important point. It's a consequence of the Cauchy-Riemann equations, which is that if f is analytic, then actually their real parts and imaginary parts are both harmonic. Right, and they're not just harmonic, but they're harmonic, and they have to satisfy certain equations between them. Okay, so maybe let's write this as a theorem. I haven't quite proven the theorem because I haven't proven that I can take two derivatives. Okay, but what we saw is if f is analytic, we write f is u plus iv, then u, I mean, I did it for u, but it's, housekeeping to do the exact same thing is the exact same thing for v. So then U and V are harmonic. Okay, we haven't quite proven this because we haven't proven that I can take second derivatives, but it will be true. Right, so okay, and moreover, they'll satisfy these equations, right? And so it'll be good to define it this way, to have a definition which we say when two harmonic functions satisfy these equations, then we say they're harmonic conjugate. Right? So if U, let's say, okay, so let me define. If U is harmonic, right? Harmonic just means Laplacian 0. Then V harmonic that satisfies the Cauchy-Riemann equations, right? So maybe let's write them again. So the derivative of U with respect to x is equal to partial derivative of V with respect to y, and partial derivative of U with respect to y is equal to minus partial derivative of V with respect to x is called an harmonic conjugate. Again, there's a whole theory of harmonic conjugates that one can build. Okay, so now, okay, I have 2 minutes. Let me leave you with the challenge, and then I'll stick around a bit to answer questions and so on. Okay, so notice too, right? If it's maybe important to point this out, right? That if something has a harmonic, the only we got U and we proved that U is harmonic. The only thing we used was the Cauchy-Riemann equations, right? So for something to, right? So something having a harmonic conjugate is very, very strong, right? And in particular, you don't need to imply that it's harmonic to start with. And so let's say that, okay, so challenge, okay, or homework, okay, if say U and V are harmonic conjugates, okay, in fact, all you need is UV to be C1, and it's enough. But you can, for now, I'm not too worried about regularity. Assume whatever level of regularity you need. UV are C1 and satisfy Cauchy-Riemann. Okay, then f of x plus iy equal to, right? So let's do this properly. Right, this is the right way of defining, you know, to be, since I'm asking you to do it, then I should be a bit more precise. Right, is analytic. Okay, so think about this at home, and then we can discuss it a bit on Tuesday, or maybe in the exercise session. Then actually, this sort of completely characterizes harmonic analytic function, right? So if U and V harmonic conjugates, then you know, and in fact, all you need is that they have the continuous derivatives and satisfy Cauchy-Riemann equations. Then it must be that they form an analytic function. Okay, and then okay, challenge 2. Take U of xy to be x squared minus y squared, right? So this is clearly a harmonic function, right? Second derivative of this is just 2 minus 2, right? And now find the analytic function that corresponds to this, right? Find V that is harmonic conjugate, and this is in the book, so try to do it without looking there, and find what analytic function it corresponds to. Okay, all right. Sorry, I took a couple more minutes. I'll stick around for questions in case there's any questions.